100 DERs while ensuring high reliability, plant uptime, and economics. Now let's look at an example. Here we can see the microgrid providing electrical and thermal energy to a commercial and residential area over a 24-hour period. The levels of energy demand and energy production vary. This affects market prices for power supplied from the grid. When there is a high surplus of renewable energy, such as solar and wind power, the feed-in tariffs are low, presenting energy arbitrage opportunities. It's early in the morning. Grid energy prices are high, so the local CHP system covers the energy demand of the microgrid, while surplus renewable energy that is stored in the BESS is exported to the grid to generate revenue. When the CHP system is running, thermal energy is stored until heat is needed in the district. As the sun rises, solar energy production ramps up, energy prices decline, and the CHP system shuts down. Local solar energy and cheap energy from the grid are used to cover the energy demand of the microgrid, while also charging the BESS for later use. The dispatchable CHP system kicks in to provide the remaining energy required. With the microgrid's power requirements met by the wind and CHP, it can once again export the stored surplus in the BESS and any renewable energy to capitalize on high feed-in tariffs. Later that week, the weather worsens, and eventually, a severe thunderstorm develops. Lightning strikes a nearby power line. Leading to grid outage. Within milliseconds, the microgrids to the BESS while ramping up the CHP. Because of the super-fast response of the BESS and the inertia of the CHP unit, this switch happens with minimal frequency and voltage deviation. Thanks to the seamless transition, microgrid operations continue without any noticeable disruptions. Eventually, the grid failure is resolved, and the microgrid reconnects and synchronizes back to the main grid. The microgrid is now back in grid parallel mode.